So proving the sine law, because their sine law looks like this. And the letters don't matter in that you could have had your triangle labeled with L, M, and N. It doesn't matter. The key thing in the sine law to recognize is that I've got big B going with little b, big C going with little c, big A going with little a. And remember how angles and sides are measured? That means something is always going with its opposite side, an angle in its opposite side. So I really don't stress that you have to know what the letters are, but instead think about every time I have an angle, it's going to go with the opposite side. Okay? And you can choose with the sine law to either have the sides on the top like I have here, or you can have them all flipped and it's still all equal to each other. So it doesn't matter, but again, the angle goes with the opposite side. So if we took a random triangle here, and I label A, B, and C, then this side here would be little c, this side here would be little a, and this side here would be little b. Okay? The way to prove the sine law, well, it uses sine, and our definition from last year for sine is opposite over hypotenuse. But that only works with a right angled triangle. So what we do to prove the sine law is we draw in the height of our triangle, make a 90-degree here. Are you okay if I use h, or is that going to confuse you because h sounds like hypotenuse? Should I use a different letter? Okay, well, why don't we just call it x? The height of our triangle is x. So now, I just drew a right angled triangle. By drawing that right angled triangle, I still have angle B here and angle A here. And if I talk about one right angled triangle, would you agree that sine of angle A, the opposite side is x, the hypotenuse is little b? Good? And if I talk about the other triangle, I could have sine of B is equal, and now my opposite side is still x. My hypotenuse for this right angled triangle is A. I can get x by itself in both of these. If I multiply this one, both sides by b, I get x by itself. If I multiply this one, both sides by a, I get x by itself. A little bit of substitution. If one equation is equal to x and the other equation is equal to x, can you see that both of these are equal to each other? And with that, if I divide both sides by b and I divide both sides by a, can you see that dividing both sides by b would get rid of the b on this side, and now I would have the b on the bottom there, and dividing both sides by a will get rid of the a on the right side, and you'd have dividing by a over there. And we just proved that sine a over a equals sine b over b. Now, whenever you use the sine law, you look back at the beginning, it has three parts. It's also saying that it's equal to sine c over c. Well, I showed that sine a over a was equal to sine b over b by making this the height of my triangle. But if I decided to draw a 90-degree here and make this my x, I could prove exactly the same way. Sine b over b is equal to sine c over c. And then if you have that sine a over a equals sine b over b, and then you have that sine b over b equals sine c over c, you have all three of them. Sine A over A equals sine B over B equals sine C over C. But when you're using the sine law, you will just use two of them at a time. So it's a little proof of where the sine law comes from. It's just SOHCAHTOA and then rearranging to get rid of the side that you don't have. You never have that x. So you can work with it to prove the sine law, and then you don't need it anymore. And so what's nice about the sine law is it works even if your triangle isn't a right-angled triangle.